In this video, I want to review all the concepts from Chapter 3 and kind of close things up. So first, true or false, a correlation of 0.2 means 20% of the points are correlated. Well, the word correlated, that's not really a word we've used at all, and for good reason. It really has no meaning. Remember, correlation is simply a measurement on a scale from -1 to 1 of, it's false, of how linear data is, okay? When the correlation is 0, there's no relationship between the variables. That's false. There's no linear relationship between the variables, but there certainly could be another equation for a trigonometric or something that would fit the data very well. When R is 1, there's a cause and effect relationship. No, correlation does not imply causation. So even if all the points lie in a line, we can't make the leap to say that the X variable causes the Y variable. And the reason is, remember, in correlation, we can switch the variables and get the same number. So how can there be a cause and effect when you can switch the variables and get the same number? Correlation is resistant. That's false. Outliers will greatly affect how the data appears linear. And the least squares regression line is resistant. That's also false. That would be greatly affected by outliers and influential points. Suppose the mean of the mean X value is 17, deviation 3.1, the mean Y value is 24, with a deviation of 6.2, and the correlation is 0.856. First, find the least squares regression line. Well, remember, the way we find our slope is correlation times SY over SX. So for us, that will be 0.856 multiplied by 6.2 over 3.1. So that's 1.712. Okay. And the way we get our y-intercept is we use the means. We do y bar minus b times x bar. So for us, that will be mean y was 24. So a equals 24 minus 1.712 multiplied by the mean x value. So 17. And that is negative 5.104. So my regression equation is y hat equals negative 5.104 plus 1.712x. Predict for when x is 22. All right, so for that, we'd simply plug 22 in for x, so 5.104. I'm just going to erase that dot. Plus 1.712 multiplied by 22. If I do that on my calculator, I get 32.56. Like that. And if y is 29.6 when x is 22, find the residual. So if this is the actual value that actually happened, remember, to do the residual, we do the actual value minus the predicted value. So we would do 29, the actual value, minus that predicted value we calculated, 32.56, and we would, 29.6, excuse me, minus, and we would get, so scatter plots. If you remember back when we were doing kind of this one-dimensional data and we'd look at box plots or histograms or stem and leaf, we had cus. Well, now for scatter plots, we've been using DOFs. Okay, DOFs stands for direction, outliers, form, and strength. So I'm just going to kind of talk through this if I can. The direction, it seems very positive. We seem like we have a positive association going through this. Outliers. Well, let me quickly just kind of sketch in what I think this line of best fit, this least squares regression, would look like. The only outlier we have is this point up here. This is an outlier. It's far away from the line. This point up here is, to me, an influential point. We had a positive trend. We could see that the data was trending positive, but this makes the line look very, very strong when we connect it to that point. So we only have the one outlier. The other is an influential point. The form, I think a linear equation fits the best. And strength, well, without the outlier, if you ignore that, it's very strong. Okay, the outlier weakens it, but it's a strong positive correlation. So what does the slope mean? And how do we interpret it? Well, what the slope means for us, remember, we kind of have that fill in the blank kind of definition for each additional explanatory, and I'm going to just kind of write that as an X. The Y, or response variable, is predicted to, and then we put in the number for the slope. Okay, so for every additional explanatory, what is the response predicted to do? Now, slope is or is not the same as correlation. It is not the same. What they will have in common is their direction, or they'll both, the sign, they'll both be positive, they'll both be negative, but you shouldn't assume they're the same thing. It would have to be a very strange case for them to be the same. Of course, if you think about the formula, what would make them the same is if both the explanatory and response variables had the same exact deviation. Okay? And that would be a really weird situation. Correlation. A correlation of 0 means that there is no linear relationship. Okay. A correlation of 1 or negative 1 means that all the points are on the same line. Okay. Of course, with positive 1, it would be a line with a positive slope, and negative 1 would be a line with a negative slope. But a correlation of 1 or negative 1 does not mean we have a cause and effect relationship. All it means is that the points are linear. If we switch the explanatory and response variables, what would happen to our correlation? Nothing. Okay? Correlation is simply a measure of how linear the data is, and changing your x and y will not affect that. The meaning of r squared, well, remember, the r squared is called the coefficient of determination. Coefficient of determination. And the meaning is, it is the proportion or percent variation in your response variable, I'm going to put y, that can be explained by variation in x, or the x variable. Okay, the percent variation in, it should be in, let me change it, in y, that can be explained by variation in x. So, linear regression. Let's kind of make a distinction here between linear regression and correlation, because linear regression does need an explanatory response relationship designated. And if you switch your explanatory and response variables, you need to make a new regression equation. They won't stay the same. Okay? We need to decide which one we think we're trying to, use to predict the other one. And how do you interpret the y-intercept in context? Well, if the explanatory, or the x, equals 0, the y is predicted to be whatever the y-intercept is. Okay, so it's what happens when your explanatory variable is 0. What's the response predicted to be? Remember, with both slope and the y-intercept, the key word there is predicted, right? It's what we're predicting will happen. A residual. So what is a residual? Well, the simplest way to think about it is a residual is the difference between the equation, or I'm sorry, the individual points on the line. And we always do it with it's the difference between the actual data point and the predicted data point. Okay, so what was on the line? So another way to think about that is that it's the actual y value minus the y hat value that we got from our line. The mean of the residuals. Well, if you added up all the residuals and divided by how many there were, the sum of the residuals is 0. So because of that, if you were going to find a least squares regression line through your residuals, it would look like the axis. It would look like y equals 0. Remember, the thing we look for with residuals, we look to see if there's a pattern. So for example, if I just drew a couple of quick residual plots like this. If you had something that was like this, it's kind of an even scatter of points about the line, that's good. This is what we want. We'll make a little smiley face. Okay? That's a good residual plot. That means the line seems to work. If we have something like this, that's a pattern, and we see a trend, that's bad. That means we could find something better. We could find an equation that works better. And another situation is something like this. What this symbolizes to me is that at the beginning it's a good plot, and as time goes on, our equation fits worse and worse, and we would really not like to use this to predict then out in the future. Okay, so those are some situations with residual plots to look for. And finally, computer output. Okay, now I found some computer output here that actually included the equation already. Of course, this should be cost hat, but it's a cost versus income. But that's okay. It gave me a chance to just point out, the y-intercept. This comes from the constant line, and the explanatory variable is always listed right next to the slope. So you'd have 0.51145 times income. Okay, so cost hat would equal that. So that's how you find the LSRL, is the y-intercept is next to constant and the income is next to, the slope is next to the explanatory variable. Of course, how do you find correlation? Well, you're given r squared. So, of course, you could find r by just doing the square root of that r squared proportion. And finally, S. You see this value S over here. What S is it represents what we say is a typical difference between the data points and the line, the regression line. Okay, so it's in a way it's a standard deviation, right? Standard deviation we always think of as being kind of that typical difference between individual data points and the mean. Well, this is the typical difference between the individual data points and the regression equation. Okay, so it's your error, your kind of residuals error.